everyone. This is the lecture for section 7.2, the calculus of parametric curves. So in section 7.1, what we handled was just how to define curves parametrically, right? So now we know that not only do we have explicit methods of expressing a function of some sort, right, or a curve of some sort, we now have parametric equations to sort of express our curves, okay? So now that we know what parametric curves do, right, we'll start hitting it with a bunch of our Calc 1 stuff and our Calc 2 stuff and start making sense out of it that way, okay? So the first thing I want to do is just define how to take a derivative of one, okay? So the definition of the derivative of two curves that are defined parametrically, right, is that, first of all, assuming that the derivative of the x of t is not 0, then the derivative is just this, the y prime of t divided by the x prime of t, okay? And the way that this works out is because of chain rule. That's it, okay? So let me go ahead and give you guys a couple of examples here. So let's go ahead and take the example that we had from our previous class, right? From our previous lesson, the parabola. Okay, what should the derivative of the parabola be, right? So it's going to be, you know, the y. Whoa. Let me switch pens. Yeah, it's the y prime of t divided by the x prime of t, right? So my x prime. Let me do my y prime, right? My derivative of y of t is going to be 2t over the derivative of x of t. That's going to be 1. So 2t, all done. I know this looks way too simple. And it turns out, yeah, it is. Bam. Okay. Next one. So again, we're using the same examples from the previous section, right? We know that this is supposed to be a circle, right? So let's go ahead and try to find the derivative of this now, right? So it's going to be just how it is up above, right? So y prime of t divided by x prime of t. So my y prime of t, right? My derivative of sine is cosine, so it's going to be 4, right? Whoops, not sine, cosine of t over the derivative of 4 cosine. So the derivative of cosine is minus sine, so 4 sine t negative this time, right? So then all of this sort of semi-divides out, right? And you get left with cosine of t over negative sine of t, and that is negative cotangent of t. And we are done. Okay, not bad, right? Not bad. Okay, so the same thing that we were doing in Calc 1 can be done here as well, finding tangent lines, right? Equations of tangent lines. And we can do them to specific points, right? So let me take this example, right? So I have two parametric equations, right? And I want the tangent line at a specific t value, right? At a specific t value, t equal 2, okay? So if you guys recall, right, when we do the equation of a tangent line, right, we're looking for a y equal mx plus b. So we need to find these two things. We need to find the m and we need to find the b, right? So let me actually grab that. I do want to eventually put some stuff here. So the first thing I'm going to do is I'm going to need to find, right, if you guys remember back in the day, right, the slope we ended up getting, so the slope 1, right, we ended up getting from our derivatives, right? So we'll save that for a little bit. And then b, we needed a point in order to, because once we had the slope, we needed a point to find our y-intercept, right? So that's what we're looking for right now. So we wanted at a specific time t equal 2, right? So x of 2 is going to be 2 squared plus 1. that's 5, right? Y of 2 is going to be 3 times 2 minus 1. That is also going to be 5. So my point in this case is going to be 5, comma 5. All right. Now let's go ahead and do our derivative, yeah? So m is going to be my y prime of t, right? Over x prime of t at a particular point, right? So the derivative of the top, the derivative of the y of t, right, is going to be 3, because it's the derivative of 3t minus 1, right? Divided by the derivative of x of t. So the derivative of t squared plus 1. That is going to be 2t. Okay. Now my m, right, at t equal 2, we just get to plug it into here, right? So it's going to be 3, 2 times 2 is 4. So the slope, this is going to be my m. My slope is going to be 4. Okay, so now we're sort of off to the races. We're ready for this, right? So y is equal to mx plus b, right? At 5, comma 5, right? At my point, with m equal 4. So now I get to fill this in and solve it out. So 5 is equal to, whoops, not 4. M is not 4. Ha, look at me go. 3 over 4. M equals 3 over 4. Oh, good Lord. 3 over 4 times 5 plus b. 5 is equal to, that's 15 over 4 plus b. And if you solve this out, b should be equal to 5 over 4. So my slope of my tangent line, right, or sorry, the equation of my tangent line is going to be y is equal to 3 over 4x plus 5 over 4. And we are done. Okay, so again, for kicks and giggles, let's go ahead and open up Desmos. And we'll do a split screen here, right? So we'll maintain the split screen. I'm going to go ahead and get rid of those. And I'm going to go ahead and do here t squared plus 1, comma, 3t minus 1. And I'm going to go ahead and make this go from negative 10 to 10. So now let's go ahead and see what this graph looks like. This is a sideways parabola, right? So now, if you remember, right, way back from your pre-calc days, and maybe from some of your calculus days, right, this is not a function, right? This is not a function, right? Because it doesn't pass the horizontal, the vertical line test, right? But now we have a nice way, right, of representing things that are not functions, and we can do so parametrically, right? That's one of the nicer strengths of having parametric equations, okay? So now let's go ahead and finish up the rest of this problem, right? We found the tangent line, that thing right there, right? We found the tangent line, and it's supposed to be tangent right here at this point, 5, comma 5. If you guys can see at this point right here, yeah? So just to double check, I'm going to go ahead and put my new equation into the bottom. So y is equal to 3 divided by 4x plus 5 divided by 4. And lo and behold, that looks pretty darn tangent to me, right? So just to sort of drive home the fact, I'm going to grab this, I'm going to snip it. I'm going to go ahead and put that in with our notes here. I'm going to put it over here, paste it. The funny thing about our, I don't know if any of you guys use OneNote, but I do, and I use it a lot. It's the most, like if I need to write something down or correct something like ASAP, I can do it like really quick. I don't have to do like really quick, changes, or don't have to make sure that I need to submit something else for it. None of that junk. That's why I like it so much. But there are these little things. So There it is. So my y equals mx plus b, this line right here, right, is in fact tangent to my purple line, my purple parametric curve. Okay. Okay. So now what comes up for you guys is the same thing. So let me actually, there we go. Okay. So I want you guys to try it out now. Okay. For all of these, you're gonna either require a you know, really spicy versions of maybe product rule or quotient rule or power rule. Okay. I want you guys to find the equations at the times provided. Okay. Okay. So moving on. Now let's get to some heavier stuff. Okay. The area under a parametric curve and the arc length for a parametric curve. Okay. So it turns out the theory for it is still the same as we were doing in the past. Okay. So the first thing I want to do is this. Let me go ahead and define what the integral using parametric curves is supposed to look like, right? Suppose you had two parametrically defined functions, so an x of t and a y of t, right? Then the area under the curve is given by this integral right here. Okay, and like I said, the theory is still the same, right? So if you remember when we needed to find the area under a curve before, when we had an f of x, right, is that we grabbed our interval, our x interval, right, from a to b, and we divided it up into smaller little chunks, right? We found the areas of rectangles, right? And then we grabbed all those areas of those smaller rectangles, added them all up, and that ended up giving us an approximation to the area. And then we let those slivers, those small little rectangular slivers, become infinitely skinnier by taking the limit as n goes to infinity. If you do that same construction, exactly the same, you end up getting this right here. Okay. I don't want to go through the construction. I think it's much better if we go through the construction for the arc length. So let me go back to the arc length. So if you guys remember the arc length back when we had an f of x, right? It was this thing right here, right? And the way that we got that thing, right, was we divided up our curve, right, into smaller little sections, and we found the distance between any 2 points. So we had that thing, All of these were equivalent, if you remember that, right? Okay. In particular, I want to look at this thing, the thing that I'm going to leave in yellow, highlighted yellow. Okay. So if you look at that thing, right, we get this right here, right? And if you remember how the construction for that went along, right? What we ended up doing is we grabbed our x interval, right? And we divided it infinitely finer and finer. So we let the delta x, right, become very small. And the way we did that was we let n go to infinity, right? Okay. But now we have parametrically defined equations. So how does that work? So it turns out you guys see these two terms right here, dxi and dyi. That's essentially telling us to take the derivative of xi and yi, right? And we know how to take derivatives of each one of those already, right? Since they're defined by t, right? That leads us to the construction of the arc length equation from below. Since now that we have them, since now that we have our equations defined parametrically, right, we get to take the derivatives with them in terms of t. Okay. Okay, so let me go ahead and scooch down here, right? So actually, let me not go that far down yet. Let me keep that equation up here, right? So Find the arc length of the curve defined by the following parametric equations over the interval provided. So let me go ahead and let's go to Desmos here, right? I'm gonna get rid of that and get rid of that. I'm gonna go ahead and graph these two, right? So 5 cosine of 2t, comma, 5 sine of 2t. Okay, and I want them from 0 to 4 pi. 4 pi. There we go. So here is the parametric curve that we just sort of graphed, right? Now, notice how I did it from 0 to 4t. I'm going to go ahead and cut it in half. I'm going to do 0 to 2 pi. Notice nothing changed, okay? Let me go to pi. Whoops, just pi. Okay, notice that is now nothing changed still, right? But now what I'm going to do is this, and this is something that you guys might want to, maybe you might want to employ here and there. So instead of t, I'm going to call it a, and here there's a reason why I want to call it a. And I'm going to add a slider here, okay? And what I'm going to do is I'm going to add a label. You see how it showed up a point here, right? So now I'm going to do this, 0 to 4 pi. So I'm going to let this slider run from 0 to 4 pi, right? So at 0, if you guys see, yep, there we go. At 0, if you guys see, it's all the way over to the right-hand side of the circle, right? So now I'm going to run it across from 0 to 4 pi, and you guys are going to see that circle. It's going to go once around, twice around, 3 times around, 4 times around. So the area of this arc length should be, right, going around a circle 4 times, right, with the circle being of radius 5, centered at the origin. Got it? So let's go back to our problem. Now we know what our answer is supposed to be, right? We know that our answer is supposed to be some 4 times around a circle, right, of radius 5. That's supposed to be our arc length, right? So let's go ahead and now and go and try and compute it using the equation that's above it, right? So I'm going to go ahead and I'm going to actually do it below here. So x prime of t, right? It's going to be the derivative of this thing, x of t, right? So if you do that right, negative 10 sine of 2t, y prime of t is going to be 10 cosine of 2t. So now, my arc length is going to be the integral. I need it from 0 to 4 pi, so I'm going to go ahead and do that, 0 to 4 pi, right, of the square root. Give yourself a fair amount of space for this one, because we're going to be the x of t derivative squared and the y of t derivative squared. So this is going to be the x of t, so negative 10 sine of 2t squared plus 10 cosine of 2t quantity squared. And I didn't end up needing that much space. So let's go ahead and whoosh, right, dt. Now, integral from 0 to 4 pi. Each one of these 10s, right, is going to get squared. That produces 100, right? Both of the terms have 100 in them, so I can factor out 100 from the whole entire expression inside the square root, right? I can pop out 100 from both. Then that 100 is being square rooted, right? So what ends up happening is I get this, just 10 times, run it through if you need to, right? Sine, actually, let me do it this way. Sine squared of 2t plus cosine squared of 2t dt. Okay, hopefully you guys sort of picked this out already. That is a trigonometric identity. That is going to always be equal to 1. So it's going to be equal to the integral from 0 to 4 pi of 10 times the square root of 1, which is 1. So I'm just going to not write it. 10 dt, right? And this integral is now going to be 10t evaluated from 0 to 4 pi 40 pi. We are done. Okay, now let's just, for kicks and giggles, right? We know that this is supposed to be, let's go back to our graph here, right? This is supposed to be a circle of radius 5, and we're going 4 times around it, right? So let's go ahead and do, so the circumference, right, is 2 pi times the radius, which in this case is 5. So 2 pi times 5, 10 pi, right? So that's the circumference of one way around a circle of radius 5, right? And we did it 4 times. So it should be 10 pi times 4. And lo and behold, at least all is right with the world, right? So this and this, right? They're both equal. We're good. We're good. Solid. Awesome. Okay, so now let's go down here. Let me do this next example. This one's going to be a little long. So, and I mean long, you're going to have long expressions, okay? This section and the next section are going to be working your trigonometric identities like crazy. Okay, so I'm going to erase those. I'm going to go ahead and put my x of t and my y of t. So, oops, there we go. 5 cosine of t minus cosine 5t, comma, 5 sine of t minus sine of 5t. All right, and oh, it says I need to go to a meeting. Miss. All right, cool. Negative 10. Actually, I'm going to do negative, well, let me do negative 10 to 10, just so you guys see what this thing is doing, really. So the graph of this thing is this 4-leaf clover looking thing. Okay. Hopefully you guys see it. And I only want it, so the whole entire graph, right, is a 4-leaf clover. So now let me just do from 0 to pi over 2, right? So I'm just going to go ahead and go 0, right, to pi divided by 2. So if you guys are taking a look here, right, this is just one of my clovers, right? One sort of stem of my clover. So what the question is asking us for here, right, is to find the length, the arc length of that curve, right? The length of just one of the 4-leaf clovers. Got it? Okay, so let's start. Okay, so like I said, this problem is really long. It's going to test you on a good handful of our trig identities from pre-calc. So just keep that in mind. Okay, so let me go here. First thing I'm going to do is just define my x prime of t. So it's going to be the derivative of this top thing, right? So it's going to be 5, whoops, negative 5 sine of t plus 5 sine of 5t. So this one has just your good old regular derivative. The second part is going to require chain rule, so just make sure you're up on that. Y prime of t, right, is going to be 5 cosine of t, right, minus 5 cosine of 5 of t. Okay, same thing. Is going to require some chain rule, your run-of-the-mill derivatives of additions and subtractions. This is what you're supposed to get, okay? Again, we're going to go back to our equation for the arc length of a curve. So it's going to be the integral from 0 to pi over 2 of each one of those derivatives. So I'm going to put the square root here, but I'm not going to give it the roof yet. Okay, write it out. -5. So I'm going to do the x one first, right? So 5 sine t plus 5 cosine of 5 of t squared, right? Plus my y prime of t squared. So it's going to be 5 cosine of t minus 5 cosine of 5t squared. And now I'm going to put the roof over it. Boom, dt. Okay. Hopefully that didn't scare very many of you. I know it probably did, right? Work it out. Work it out. If you need to sit there and write it out, do it. Okay. Let's move on. This is equal to the integral from 0 to pi over 2. Now, if you notice, right, everything's got a 5 in it. And all of those 5s are going to be squared, right? And each one of these two terms, both of these, right, are going to have 5 squareds up front. So I can pull out a 5 squared from each one. And then I can pull it out in front of the square root, obviously with the square root with it, right? And I'm going to have the square root of 5 squared. So the square roots and the square cancel out. So this now reduces down to 5 times the square root. So let me not put the roof on it again. Minus sine t plus, whoops, not that, sine of 5t quantity squared plus cosine of t, right, minus cosine of 5t squared. Now I'm going to put the hat on it. Boom, dt. Okay. Work it out. Okay. Write it out so that you can sort of prove to yourself that that 5 actually, sure enough, pops out. Okay. Okay. Here comes the train. Watch this. So I'm now going to expand all of this. I'm going to expand all of this, this whole entire square root. Okay. Write it out. Okay. Integral from 0 to pi over 2. 5 times the square root. So if you do this first thing, it's going to be this. It's going to be sine squared of t, right? Minus 2 sine t sine 5t. Okay. Plus sine squared of 5t. Plus, now I'm going to do the same thing now on this side. So let me do some underlining here. I'm going to do green. All of this ends up being, actually, let me not do green. Let me do baby blue. All of this is all of this. Okay. If you need to do it, do it. Okay. If you need to do it, do it. It's going to take you a while, but it is there. It's there. So now I'm going to do the next one. So that one is going to be cosine squared t, right? Minus 2 cosine of t cosine of 5t, right? Plus cosine squared of 5t. And now I'm going to put the hat on the big, huge square root. Sorry for the upward slope of it all, dt, right? So now this purple thing is this right here, if you expand it out, okay? So now, let's keep going. Equal to the integral from 0 to pi over 2. That 5 is there. So now, I want everybody to take a look at this. We have a sine squared t and a cosine squared t. okay? And then we have a sine squared of 5t and a cosine squared of 5t, okay? When you do those two, you end up getting 1 for each one, right? So then all of this now reduces to, let me not put the hat on it yet, 2 minus 2 sine t sine 5t minus 2, and actually let me go ahead and do those two so you guys see this. It's a minus 2 times that and a minus 2 times that, right? So both of these I'm going to just sort of slap under one big parenthesis. So it's going to be sine of t sine of 5t plus cosine of t cosine of 5t. Ooh. And parentheses. And now I'm going to put the hat on it. dt. Okay. Here is where it's going to test your trig skills. Okay. If you, hopefully you guys sort of recognize this right here, right, is the sum or difference of, it's the sum or difference of trig terms, right? So let me go ahead and show you guys where I'm going to go ahead and look up that portion in particular. So notice how it is. It's sine, sine, plus cosine, cosine, right? So I'm going to go back into my notes. I'm going to scroll all the way up to the top where you see calculus handouts and resources. So one of the things I put in here is a trig trifold that you can find in the tutoring center downstairs in the math lab if you're ever there. And what we're going to need is this one. It's one of these 4. It's one of those 4. So if you remember, it was cosine, cosine plus sine, sine, right? Or sine, sine plus cosine, cosine, right? That's right here. So all of that stuff reduces down to something very simple. It's going to be the x minus the y, right? So let's go back to our notes. 7.2. All of that, right, reduces down to, and I'm going to go ahead and draw it in right here, integral 0 to pi over 2, 5 times the square root come on. Let me not put the roof on it yet, yeah? Okay. 2 minus 2. And now we get to combine this. So it's going to be t minus 5t. So I should be minus 4t. So this is going to be cosine of minus 4t dt. Okay. Equal. I have that 5 up front, correct? And then I have a 2 in each one of these, right? So I can factor out a 2 inside the square root, and then I can factor it completely out, keeping the square root. So now I have this, right? 5 square root 2 times the integral from 0 to pi over 2 of the square root of 1 minus cosine of 4t. Now, the negative inside the 4t, right here, cosine is an odd function. Or sorry, cosine is an even function. So that means the negative of the cosine of a negative thing is the same thing as its positive thing. So that's why the negative disappeared here. Again, go check it out in your trig material. It's there. It's there. I know it hurts to go back there sometimes. You're thinking, oh, I took the class. I did well. and then I throw things like that at you, and you're like, oh man, I don't remember anything. It's okay. Go check. Use the Einstein method. Don't memorize anything you can look up. Okay, so integral 0 pi over 2. Now I'm going to handle this thing. I'm going to handle this. I'm going to try to get some sort of answer for that. Okay, and I didn't want to, there we go. And then that's supposed to still be dt, sorry. So equal, okay. This is gonna hurt again, okay. I'm gonna do some magic here. I actually got ahead of myself here. 5 root 2 integral 0 to pi over 2. Okay, 1 minus cosine of 4t, right? And this is all under a square root. What I'm going to do is this. I'm going to divide it by 2 and then multiply it by a root 2. Okay, so what I did here is multiplied it by 1. I multiplied it by the square root of 2 divided by the square root of 2. Okay, and the reason why is this right here is also a trig identity. This is actually one of our half angle formulas. Okay, so let me show you guys which one I'm talking about. It's not exactly, there's going to be a little bit of a modification that I need to make, but it's there. Let's go back over here. Hopefully you guys have picked it out already. Minus. Okay, so we're going to take that knowledge back into our notes. Okay, so now, and this is still going to be dt. I have a root 2 and another root 2. So now these two root 2s, they get to combine and make 10 with the 5 up front. So it's going to be 10, 0, pi over 2. And that thing in the square root is now going to be sine, right, of 2t dt. So that thing in yellow becomes this thing right here. Equal 5 times 2, that's my 10, right? 10, and this is going to be the integral of sine is negative cosine of 2t over 2, evaluated at 0 to pi over 2. Okay. This gets to make it a little nicer. So I'm going to have, and did I forget a negative? No, I did not. So it's going to be negative 5 cosine 2t evaluated from 0 to pi over 2, right? Negative 5 cosine of pi over 2. That's going to be pi, so it's going to be negative 1, right? And then cosine of 0 is going to be another minus 1. Minus 5 times a minus 2, 10. And we are done. I know it sounds weird to have a nice round number for so much work, but it is correct. We're good. Okay. Now, what I want to do is I want to show you guys, because I'm still logged in, you can still use, I know we haven't used it too much, but we can still use this to solve this thing out. Remember, this is a general calculator now that can give you the integral from whatever point to whatever point you're looking at, right? Now, you do have to simplify a little bit of it, right? So I'm going to go ahead and put in this thing right here, okay? Well, you can put in anything so long as it's equivalent, right? So let's actually, you know what, let's go ahead and put in 5 square root, right? 2 minus 2 cosine of 4x, right? There we go. Okay, and in particular, right? So basically, I put in this, no, not this one right here. I put in this one right here for our computation. Okay, and we want it from 0, so I'm going to do 0 to pi over 2. Ta-da! So the answer that we're supposed to get, if we did this, right, if we did it right, should have been 10. And lo and behold, it's 10. We're good. We're golden. We are excellent. Okay. So, like I said, you can still use this definite integral calculator to find an answer, okay? Just in case, right? All right. So what I want you guys to do now is I want you guys to try these out. Okay, use the same stuff that we were doing just now. Okay, try them out. This will work you a little bit in terms of your trig identities and stuff like that. Okay, so just keep that in mind. Okay. All right, and what comes up next is lecture questions. Lecture questions. Okay, so if there's any questions on this stuff, you know where to find me. I have my office hours where you can stop by online. I'm in the math lab, or I have my all day Friday hours. So choose one of them. Come drop by. Okay. Besides that, I am done here. Happy studying.